So the case of for quantum computing, and now let me make it the case that quantum computing is very similar to the two examples that we have seen, and in fact, I will make the case that quantum computing in some way is very close to the two great sciences that I have mentioned. In fact, quantum computing itself is the interaction between the two examples that I have mentioned, X-ray crystallography and computer science. And now, let me tell you what the disruptive technology is in this case. It's mainly that for quantum computing, there is a new computing paradigm that is very different from the digital computer that we are used to. And in fact, it is a throwback to the pre-digital computing days, pre-Turing days. It goes back to saying that if you contemplate the question, what is a computer? Then there is a branch there. Turing and many others took one branch, saying that it's essentially a digital computer. But actually, you could have taken another branch. It's saying that you can take a more general view by saying that a computer is simply any physical devices that is capable of processing signals. And the question is that in most cases, you will not be able to extract more knowledge than the digital model. However, the possibility remains there. And it's the last 60 years of great success of electronic computer during those times made us oblivious to that possibility. But now quantum computing is bringing it back. It's saying that let's go back to see what does nature have in store for us if we are courageous enough to explore it further, to forget about the digital processing. Are there more powerful things we can do? And so this disruptive computing paradigm, let me describe it in the following way. Let's assume that you have a string X. So it's, let's say, an n-bit string or even a real number. And you would like to compute a function f of x by a Gedanken thinking experiment. And the method is that you just imagine that according to this function f and this input x, let's try to grow a crystal. So it's some sort of crystal, perhaps not in 3 dimensions, it could be 4 dimensions or high dimensions. And now let's imagine you shine a optical wave on it. And now, in principle, if the conditions is right, then you'll be able to see a diffraction pattern if you design it clever enough. So if you are lucky, you'll be able to compute this f of x. Okay, so this is a way of doing it. And now, that's the motivation coming from crystallography. And now, let's add a little bit of the quantum magic. That in classical computer, electronic computer, we know the tremendous power of software simulations. And I think that we all know that in the modern design of big jet lines, actually people most likely will use the digital simulation instead of the wind tunnel as classically constructed. It's cheaper and more accurate to do it inside a computer. And so as computer scientists, we are not it's not unusual for us to think about doing things using software instead of thinking about hardware. Now, however, in most cases, in all the cases that we are familiar with, software simulation is only a kind of, it's not, if it may save some money, it may save some time, but the order of magnitude cannot be astronomical. In other words, when we use software to simulate hardware, basically we are doing a polynomial simulation in terms of the cost that is used. However, there is a new phenomena in the quantum software simulation. Sometimes it is possible to do a simulation using quantum mechanics that can speed up exponentially over the classical hardware. So therefore, this gives us a tremendous leeway that if the conditions match, then it's conceivable that you can design a crystal optical wave experiment that is very expensive. However, if you have the availability of a quantum computer, and if the situation is such that you can do exponential speed up, then even this very cumbersome crystal Gedanken experiment can be actually carried out because of this exponential speed up. Okay, so now I'm going to show you an actual example of how this can happen. And actually, I'm going to show you essentially the secret behind Peter Shor's quantum factoring algorithm. Okay. So instead of telling you about the factoring algorithm, let's illustrate with a something that is quite similar. It's called Simon's problem, and this is a paper by Simon in 1994. And the problem is the following. Suppose you have a black box, and you do not know the inside of the black box. And but you know that the black box, the operation is such that it will take an n-bit string, and it's going to output an n-bit string. So in other words, we'll transform one n-bit string into another n-bit string. And this black box is a 2-to-1 mapping. So in other words, this black box, it is not a 1-to-1 mapping. It is not saying that for each input there's one output, and for each output there's an input. This is a 2-to-1 in the sense that for each output there are two input that can be mapped into it. So there are exactly 1/2 of the 2 to the n strings that are potential outputs. And furthermore, this mapping have a special character, namely that for this black box, there exists an unknown secret S. This S is an n-bit string. And now, the two strings that are transformed into the same output are connected by, one of them is X, then the other one is X plus S. So this is this plus is the exclusive OR of two strings in a bitwise manner. Okay, and so suppose you are given a black box with this property, and the problem I want you to solve is to determine, to find out what secret this black box has. And note that it's intuitive clear any classical method for trying to determine the secret S will need exponentially many queries. You have to run this black box exponentially time, because if you don't run, if you don't try an exponential number, this black box will essentially behave like a 1-to-1 random mapping for you. So, but now what I'm going to show you is that if you have a quantum lab, how do you solve this problem with actually a linear number of experiments instead of exponential number. And now let's review the standard setup of diffraction patterns. You have a light, which is has a single wavelength. And now on the first screen, you would drill a number of holes at regular intervals. And now on the second screen, so you let this light to pass through this screen through the many holes, just let them run. Then you're going to see that there will be diffraction patterns on the second screen. So the diffraction pattern means that if you look at the light, it will be someplace will be dark, and then someplace will be bright. And there are, in particular, there are periodic dark spots. And now, the pattern, so essentially, this pattern, in particular, the magnitude of the interval, this is determined by the particular experimental setup, namely that the wavelength of the light and the spacing of the first screen, and also the distance between the light and the two screens. Those are all parameters. You can write down the formula to calculate it. And so if you look at the second screen and you look at the pattern and say the distance between the dark spots, it tells you the value of a function of all those physical parameters. So it tells you something about it. And now in the applications to crystals, you would have the light go through the crystals, and now the crystals, the holes on the first screen will not be a simple linear arrangement, but in the crystals, the way that the light gets diffracted is that you have a periodic structure of the crystals, and this is a three-dimensional object with the atoms located in a three-dimensional way, so it's more complicated. And on the second screen, you will have a two-dimensional pattern. And again, the Nobel Prize winning is saying that what does the mathematical formula looking like, and by looking at these patterns, it tells you something about a crystal. So therefore, if you just change the light source and you move the distance a little bit around, the formula will give you a lot of information about this crystal. And if you are careful and patient, you'll be able to determine exactly how the atoms are located within the unit of the crystal. Okay, and now we are going to do something similar. But what we are going to do instead of this in the physical world, the three-dimensional crystal, given a function f and given an input x, we are going to construct a crystal that actually lives in a high-dimensional world. And in fact, let's imagine, so now we have an n-bit string, so the crystal we construct will be a n-dimensional crystal where each of these these vertices, will correspond to an n-bit string. So there are 2 to the n different vertices of this crystal. And now we have a light, and with a certain property that we specify that this light is not the ordinary light, but the way of the propagation of the light is very specific. So essentially, at each vertex x, the light after coming here is going to propagate to a specific location. So in fact, it's going to have a so light coming from here will arrive on the screen with a certain fixed vertical location determined by the output of the black box. Okay, so if you look at the pair of inputs which correspond to the same output in the black box, they would going to travel to the same location. And so light from these two places, they are going to be able to interfere with each other. So if you construct a light wave such that the location have that property and the amplitude has this property, and then after some calculation, you will be able to find out that here is the following phenomena, namely that if you only look at contributions from one vertex, it's going to have all the points on the line, they will be lighted. But if you consider the light coming from both of these vertices, then half of the points on the line will go dark because of interference. And where it is bright and where it is dark will tell you quite a bit of information about the nature of f of x.